You're welcome. All right, so we're still working with volumes of solids of revolution. You're still going to have a region that is being rotated around an axis. What I have here to start is just right away with an example so that you can visualize or see why these regions are different than what we had yesterday. So example 1, we have the region that's enclosed by two curves, y equals x to the fourth, and then y equals the fourth root of x. And it's rotated about the x-axis. And it says find the volume of the resulting solid. So you might already know what x to the fourth and the fourth root of x, what that region would look like. If you don't, you can graph it. If you need, I just overhear some of this right now. To get a fourth root, you can either type in the 4 first. If you have an 84, you don't need to. But if I type in 4 for the fourth root, and then it's math, and then it's option 5. That's where your x root key is. If you have an 84, it might change it so it actually has the correct notation of a fourth root. Yep, so 83 you might have to type the 4 first before in order for it to work out. And then I'll use the standard window, and we want the region enclosed by these two curves. We're rotating it around the x-axis. So it looks a lot like the parabola x squared and then the square root of x. It's just the x to the fourth and the fourth root just make each curve a little bit wider near the origin there. So I'm going to just sketch this on my sheet. And as you can even see if you graph this on your calculator or looking at mine, even though the x to the fourth graph is also in quadrant 2, the only part we're concerned about is the region bounded by them. It's this part right here that's in quadrant 1. So I don't even need to draw that other part. I'll just draw from x equals 0 on. So this would be y equals x to the fourth. And then this is y equals the fourth root of x. Because we'll need to know this, so we can see one intersection is at the origin. Where is the other intersection? 1, 1. Because we would need to know that when we set up our integral, what our limits of integration are for either x or for y. And this is being rotated around the x-axis. So I'm first going to show you if we take the entire region and rotate it, what it would look like, or if you are one where actually sketching it out is helpful to you. You can see what it looks like. So what it would look like is, as I draw it, I just kind of reflect this over. So this would be the reflection of x to the fourth. This would be the reflection of the fourth root. And then, because being rotated, that means the end would be a circle. So what's happening is it is creating a solid, but this part that's kind of in the middle, this is like hollow. Because this ending curve, we're rotating around the x-axis, but the x-axis isn't actually a boundary for the region. The region is bounded by something else. So like if you looked into this, this part here would all be hollowed out. So it's kind of like the edges around of it, that's your solid part. So it's not like the ones yesterday because the x-axis would have been a boundary. If you looked at the face of it, it would be completely solid at the face of it. This one is not. Okay, so that means, and actually drawing this, you wouldn't have to do that. But this is why we're looking at a washer method, not a disk method. So if I just sketched one rectangle in that region, if I rotated just the rectangle around, because the bottom of the rectangle doesn't actually touch the x-axis, it doesn't touch the axis that's being rotated around, That means I'm going to kind of draw it like I did yesterday so you kind of see that disc shape, but you're also going to get another circle on the inside here because the bottom of that rectangle is also rotating around. So you're getting that washer. It's the larger circle, but it's hollowed out in that center there. So again, it's a washer, a disc. A disc is created if the axis you're rotating around is actually a boundary of the region. Since I'm rotating around the x-axis, but the bottom boundary of the region is a different curve, that's what gives us the washer. So that's kind of how it's different from yesterday. So if I were just to draw, here's my rectangle. I'm going to draw this separate here. I do have a washer here. So thinking of kind of working through this like we did yesterday. It's helpful if you can find an expression for the volume of one washer, and then that's what you're integrating. Or rather, what you're integrating is just, again, the area of the cross-section. So the area of the cross-section is a circle with another circle cut out of it. So it's the area of the larger circle minus the area of the smaller circle. And then multiplied by the width, which is still delta x in this case. That's what gives you the volume. So I'm going to write down here V sub W for the volume of the washer. I'm going to write it a few different ways just so you understand it some different ways. So the area, again, of the cross-section, I'm going to put here area sub, and I'll put outer. So the area of the outer circle, or if you put area of larger circle, minus the area of the inner circle. So it's those two circle areas, the difference between the two, multiplied by your width, which is delta x in this case. So that means since I have two circles, I have two radii that I have to find. The area of both of these circles is pi r squared, but their radii are different. So the outer circle is going to be pi times I'll put here r sub outer squared, and then minus area of the inner circle is pi times r sub inner squared. This is kind of the formula for all of these washers. What's different from one example to the next is what your outer radius and your inner radius are. And then you'll also see it written, because both of these areas include that coefficient of pi. You could write the pi out front as well. I'll actually do that, just have pi out front here. So what we need to do for our region is figure out what's the outer radius, what's the inner radius. So here's how you figure that out. You're using, when your rectangles are vertical like this, to find both of your radii, you're thinking of top curve minus bottom curve, the bottom curve being the axis you're rotating around. So my outer radius, the large circle that you see, the radius is extending from the axis of rotation, the x-axis, up to the top curve. Not one, that would be at a specific, if I was at the end of the interval, the specific value, yes. So it would be from the x-axis up to that topmost curve, which is the fourth root of x. So that distance, top minus bottom, this would be like the fourth root of x minus the x-axis is just x, or is just y equals 0. So that outer radius is the fourth root of x. And then I have to subtract, so I factored out the pi, it's up to if you want to factor out the pi, I did, minus the inner radius then extends from your axis of rotation, again the x-axis, up to the bottom curve, the bottom of your rectangle. The bottom of the rectangle is on the curve x to the fourth. So x to the fourth minus the 0 of the x-axis, that's just a height of x to the fourth. So x to the fourth squared times the delta x. So this is what ends up getting integrated. You're taking the integral of pi times the quantity 4th root of x squared minus x to the 4th squared. Yes. Yes. Did you have a different question or same question? So I'm thinking of when you are finding, the radius is a length. So I'm thinking usually like when you're finding the height of a rectangle, for example, you're taking the top minus the bottom. So here, the x-axis, because that's what you're rotating around, that is the line y equals 0. So I'll kind of answer both questions in the same sense here. So the radius always extends from what you're rotating around, which is y equals 0. And the outer radius is from that axis of rotation to the top curve. And the top curve in this case is the 4th root of x. So it'd be the 4th root of x minus 0, top minus bottom. So that's why the 4th root of x is the outer radius. The inner radius extends from the axis of rotation to the bottom of the rectangle, or the bottom curve, which is x to the 4th. So x to the 4th minus the 0 gives us just x to the 4th for that inner radius squared. Yes. So the examples 2 and 3 are actually the same region, but rotated around different lines. So you'll see that might kind of clear up your question too when it's not just 0, it's something different. Okay, any other questions just on this setup? So this is kind of always, for every washer, this is what to follow. You have to figure out your outer radius and your inner radius. We do have 2 other examples. Like I just said, to IFR, that's the same region but rotated around different lines. So that might help clear up how to get each radius. Once you have this though, so now I can actually find the volume of the solid, and that's going to be integrating this expression. So I'm going to write the pi in front of the integral right away. So I have the integral from my boundaries, since my rectangle was vertical, everything is in terms of x. I want to use the x values. So from 0 to 1, it would be the same if we use the y values for this case. But integral from 0 to 1 of, and then integrating, I'm actually going to write the 4th root of x, though, as x to the 1/4. So I have x to the 1/4 squared minus x to the 4th squared, and then dx. And I just had the pi out in front right away. You wouldn't have to do that. I just like to get that out of the way. Okay, so that's the integral. I would definitely then, for these, you're probably going to want to simplify this first, unless you're allowed to use a calculator, to get the approximation. So I can simplify this. When I have a power to a power, I multiply them. So x to the 1/4 squared would be x to the 1/2 minus x to the 4th squared is x to the 8th. And then I would be able to find the antiderivative. So antiderivative of x to the 1/2. Yeah, 2/3 x to the 3/2 minus antiderivative of x to the 8th. And evaluate that from 0 to 1. Yeah, so if I substitute in 1, I'll just have the 2/3 minus 1/9. If I substitute in 0, it's just 0. So it's really just pi times 2/3 minus 1/9, which would be, let's see, 2/3 is really 6/9, so it'd be 5/9 times pi would be the volume of that solid. That would be the exact value. Objects like this. Well, this is just one like a volume of a solid of revolution, but what this is really showing you is if you know the area of a surface and you can state an interval that it's on, because really this is just integrating the area of the surface of that washer. If you integrate area, you get volume. So if you could put some object that you know, kind of put it in terms of a coordinate plane, you could find the volume by integrating the area. Or you could do that. Okay, example 2. So we have the exact same region. I say find the volume of the solid obtained by rotating the region from example 1, but now we're rotating it around the line y equals 2. So I'm going to show you, really, it's all about finding what is that outer radius, what is that inner radius. So I'll make a sketch. Again, I am showing the sketches. It is possible to set up the integral and everything without sketching it out. So if that part is confusing, don't get too hung up on that, but I can also certainly help if just seeing it helps you understand it better. So that same region, I'm just going to label these again. This was x to the 4th. This was the 4th root of x. And it was still, I'll label the intersections. But then what I'm also going to draw, the line y equals 2. So that is a horizontal line at the y value 2. I'm just going to dash that through here. That is the line that we are rotating that region around. So this is a case where the region we're rotating doesn't even touch the axis of rotation. That's okay. But now if you're actually drawing this to visualize it, it's going to look pretty weird. So if I kind of reflect this up, probably should have extended this a little bit more. So this point 1, 1 would be at 1, 3. This at 0, 0 would be at 0, 4. So it'd kind of be, that would kind of reflect up, and you'd have this open, and this would be open here. So if you actually looked at this, like if it was rotated out, you could just see through it. And you do have around the outer edge, that's where your solid, your volume is coming from. Okay? So it looks weird. Now you can, like I said, as long as you sketch the region and you sketch the axis it's being rotated around, you're able to find the 2 radii that you need. So you don't have to sketch this to be able to answer the question.
Definitely helps.
Okay, does it really do? All right, so hopefully you can see why we would get a washer. If this is a rectangle in this region, obviously the rectangle does not touch the axis of rotation. That's what's giving us the washer. So this whole thing would be open there. That's the washer we're looking at. And I guess maybe I don't need to just draw a separate washer. You just need to be able to identify it is a washer and not a disc. So here we need to come up with then the volume of that one washer. So again, it's that same formula we were looking at here. The area of the outer circle minus the area of the inner circle. So we need the outer radius and the inner radius to set it up. And I'm going to factor out the pi right away. All right, here's how you get the outer and the inner radius. Again, it extends from the axis you're rotating around, which has its own equation, y equals 2. So the outer radius is actually extending from the axis of rotation down to the bottom curve. Well, it's, what do you mean it's 1? Yeah, so I'm going to just do off to the side here. The outer radius, again, think top curve minus bottom curve. To find a distance or to find a length, or think how you found heights of rectangles, you did top minus bottom when they're vertical, or right minus left if they're horizontal. So in this case, you're extending down to where your original region was, which is below the axis of rotation. So it's from the line 2 down to this bottom curve, which is the curve x to the 4th. So the outer radius, top minus bottom, is 2 minus x to the 4th. And then the inner radius, again, still starts at the axis of rotation, the 2, but now goes to the top of that region, because that's where the rectangle would be here. So that would be 2 minus that curve is the 4th root of x. You don't need to know why. Does that make sense how I got those? Okay. So then it would be pi times your outer radius squared, so the quantity 2 minus x to the 4th squared, minus the quantity 2 minus the 4th root of x squared, times delta x. That would be one washer, the volume of one washer. Yes. So then if you were setting up an integral, your exact volume would be, I'm going to keep the pi out front right away, integral from, now your limits of integration still come from your original region. It's still from 0 to 1. Okay, so those limits of integration come from the region you had initially. And you're integrating the quantity 2 minus x to the 4th squared minus, I'm going to write the 4th root of x as x to the 1/4 right away again, so 2 minus x to the 1/4 squared, and then dx. Now if you were doing this one by hand, to simplify this first, you do need to FOIL. You cannot distribute those exponents, you would have to FOIL both of these. It may not be a calculator problem. Some of you are giving me like these scared eyes. I don't know what to tell you. This is what it is, okay? I'm not making this more difficult than it should be. This is just what it is. So we have pi times the integral from 0 to 1 of, if I FOIL 2 minus x to the 4th times itself, I would have 4 minus 4x to the 4th plus x to the 8th. And then I would be subtracting, I'm going to put this one in parentheses because I'm subtracting the entire quantity. So I'm subtracting, if I FOIL this one, I would have 4 minus 4x to the 1/4 plus x to the 2/4. Okay, and the last bit of simplifying, you would just want to distribute this minus sign through. So you'd have pi times the integral from 0 to 1 of, you would end up having 4 minus 4, so those 4s would be gone. Nothing else is a like term though, so you would have negative 4x to the 4th plus x to the 8th you would have a positive 4x to the 1/4 and a negative or a minus x to the 1/2. Okay, so this would be your integral, and then you would take the antiderivative to evaluate that. Now I'm going to ask this, would you be, once you have the integral, would you be okay from here to get your answer if we moved on to the next example to set it up? Okay, so antiderivative of this, and then just substitute in the 1 and the 0 to get your value. So this, how do I do the FOIL trick?
Well, it's good. It's just 2.
So yeah, it's this squared is your last, or your first term, this squared is your last term, and then this is, if you multiply these together and multiply it by 2, that's your middle term.
If it's minus, then
You could, if it helps, just write this out. I honestly, I kind of just picture this in my head, and I still, like, I do this in my head to think through it. The shortcut, though, is, it's, yeah, if you have a minus b squared, it is a squared minus 2ab plus b squared. Or if this is plus, it just means your middle term is plus. Did you know that and you're just asking to be funny? Or what? Oh, why are you laughing?
No, I think I ran out of
Oh, you probably did. Okay.
No,
Oh, yes. Sorry. So, well, for the next one, I'll do this. The next one, I won't draw the picture just so you can kind of see it too. It is different because it's going to, I mean, there's differences with the next one. But with this one, notice the your region is actually above what you're rotating around. Whereas in the second example, the axis of rotation was above it. So here, the axis of rotation is actually, when you're finding your radius, it is the top minus the curves are the bottom. Versus here, your curves were the top and the axis was the bottom. So does that help answer your question? Okay. So here, example 3, again, same region, different axis of rotation. And I can draw the region later, but I'll just draw the region itself and the line we're rotating around without drawing the solid, and just show you can set this up without drawing the actual solid. We are rotating this time around the line x equals -1, so a vertical line. So same region. And, yep, this would be x equals -1. And we are rotating around that line. So I'm going to show you how to set this up without actually drawing it out. I can draw it later if you want to see it drawn out. This, that means to draw it out, would be reflected over here. So it would kind of look like the last one we just did, but it would be shifted around. Because on the end, 2 ends again would be open. But you don't actually have to draw the full solid to be able to set it up. You just have to be able to find your 2 radii. Now with this one, if you are rotating around a vertical axis, remember you need to, if you're drawing a rectangle, it would be horizontal, meaning everything then needs to be in terms of y. Okay, so this, and you're actually thinking right minus left, not top minus bottom. So y equals x to the 4th. This curve would actually be x equals the 4th root of y. And then y equals the fourth root of x is actually x equals y to the fourth. Okay, but you're working in terms of y. So for one washer, I'll just list this here. Let's first find our outer and our inner radii. Right minus left. Okay, so it again extends from your axis of rotation. So I would be extending for the outer radius. I would be extending all the way to this curve here, the farthest one from the axis of rotation, which this curve is the fourth root of y. And if I do right minus left, the axis of rotation is my left curve. So I would have the right curve, which is the fourth root of y, minus the left curve is -1. So I have minus -1, which really will just be the fourth root of y plus 1. That's my outer radius. My inner radius then, again, extends from the axis to the curve closest to that axis, which is y to the fourth. And the y to the fourth is the rightmost curve between these two. So it would be y to the fourth minus -1. So it's really y to the fourth plus 1. Well, it's a horizontal rectangle, so you have to have it in terms of y. Because this curve is the fourth root of y, that is the outermost one compared to this. You were looking at x to the fourth, yes. Okay, I can answer questions. I want to set this up, though, what the integral would look like, because I know we're done in a minute here. So we would have the integral from, well, actually, we'd have pi in front. We'd still have, since the intersections were 0, 0, and 1, 1, you'd have to use the y values of the intersections. And so the y values are still the same, 0 and 1. So I'd have the integral from 0 to 1 of the outer radius squared, so the fourth root of y plus 1 squared, minus the inner radius squared, y to the fourth plus 1 quantity squared, and then it would be dy. That would be the integral I would be evaluating in order to get the volume. So then, similar to the previous example, FOIL these to simplify it first, then find your antiderivative and so on. Okay, the setting up, though, is the newer part.
I know what to do if once you set it up.
Why it was minus -1?
Yeah, why is it minus?
Because it's either if your rectangle is vertical, it's top minus bottom, or if it's horizontal, it's right minus left. So my outer radius, your radius always extends from the axis of rotation to the curve that's farthest away from it. So this one would be, or between these two, this one is right, this one is left. So it would be this curve, which is the fourth root of y, minus this curve, which is -1. And then same thing for getting the inner one from the axis to the closest curve. So y to the fourth minus -1. Does that help?
That was like x equals 2.
If this was x equals 2, then it would be over here.
You want to be able to do it.
So, what?
Would you be able to do that? Rotate that?
Yes. You can rotate around any axis, yes. So if it was x equals 2, yeah, if you're good, you guys can go. There is practice there. I will go through any questions you have tomorrow.
Like across the origin?
No, it'll always be vertical or horizontal rotations.